Um, Welcome to this first example of our Python primer. As you guys know, Professor Robinson canceled the Python project. That was part of his course. I'm talked a lot about it. I really liked it. I really want you guys to go through the same stuff in that, but it's gone now. So I feel some sort of like emptiness. Like I got to let you guys see some of it, like what I went through and the previous generation went through. I hope there's some good takeaways. I'm hoping that the content I put here will reflect in class and potentially on the homeworks and quiz or and stuff like that. So I'm planning to hopefully wrap everything up within an hour. And afterwards, maybe for like the extra time left, feel free to ask me some questions about the fluid quiz practice prompts. I went through some of them myself. I have a slight grasp of what's going on, but Professor Robinson's wording is a little vague, so definitely talk to him about that. But I'm more happy to share what I understand of the quiz. Okay, so that being said, out of the way, let's go to the first content slide. So I'm Hui Tran, see up there. I'm a third-year PhD student. It's going to be a long journey, but it is what it is. And over the summer, I had a chance to intern at NASA. It was really, really great. I got to see on the left-hand side other Davis students such as Esther and Carlos. Yeah. And on the right, those are my co-interns. And I miss them dearly, but they're all in the East Coast, so can't really see them, right? So I looked on the left-hand side. It was kind of it is still surprising that I've generally seen a lot of Davis students who end up at NASA Ames at least. And it just shows that possibility does exist. Because to be honest, like when I came here as an undergrad, I thought this was impossible to like work in like places like that, right? But a lot of people end up working like here or other national labs or other big locations. So definitely keep your doors open, keep your connections up, and you might end up somewhere like that too, right? All right. So that being said, why we're here. Sorry, we're talking about Python, right? Because Professor Robinson, he's dropping the ball, so I'm picking it up for myself. So Python is a high-level programming language. That term means nothing to you. That's fine. It's very much just only using the CS world. Essentially, what they're trying to say is high-level language are meant for like people like don't really know programs. So, like it's like very basic English terminology that they're using. Whereas Python, it's more English friendly and more easier to read when you look at the code. A big difference is that for high level programming, you're moving a lot of the tedious tasks using coding. So, for example, if you look on the left hand side, C programming, C, C++, like I think Java, and some other languages require you to optimize memory usage as well as speed. So, for example, you have to declare if your variable is integer, is it a string, is it a floating number? There's all these different things that you have to optimize. And where in Python, you can assign one value integer at one time in one line, and for the following lines, you can call it a string, and it's fine. It'll just change it by itself. And so Python is mostly used for incorporating AI and machine learning packages for people to use for their work. However, Python has been pretty big for computational engineering simulations too, and I'll show you why in a bit. Okay, so today the problem that I want to tackle is basically using two-dimensional flow building blocks. This is a topic that you have covered in 116 and probably forgot about because honestly it was kind of relevant back then, but it plays a really big role now in 127. So there's some assumptions obviously being made when you use 2D potential flow. One, for example, is not three-dimensional. There's a 2D and basically an infinite length something. Also, on top of that, your flow is inviscid, irrotational, and keep it frank. It's very simple. So in 106, you may have learned that there are three main building blocks for potential flow. I have them listed down here. For A, you have the free stream, which is just a flow going from left to right. For B, it's a source. Essentially, it's just a point where flow is gradient smit. And C, that is a vortex. So around one point, your flow is just spinning circles around it. So today, we're going to tackle A and B, and hopefully next week we can get to C. So you guys have the website that I told you guys to pull up. If you have access to it, please do the following. I have these 5 libraries that we're going to be using. Please write these 5 lines down. I'll do that in a bit myself, but we're going to import these libraries. As any other coding languages work, Python has Python can do calculations, it can do math, assign variables, use variables, but it's not really useful unless you make functions or basically have like lists of tasks for it to accomplish. That's not what these libraries are. These libraries are pre-written functions by other people who are then basically made to be very robust to use in many different applications. So we're using NumPy. NumPy is just numeric Python. That's how you basically it's low key just like basic MATLAB functions, but now you can use it in Python. Math. I mean, we already do math. Mat third line matplotlib. That is basically I think it's like matplot library. It's how we plot our functions and graphs to make it look nice. We also have pandas. Pandas essentially I think most used for data science at MIS, which is like a business major, but it's very good for storing data as data frames and basically makes your organized data more readable and more user friendly. And lastly, this is kind of a random one, but from SciPy, which is like the main numerical computational Python library. And is used for if you take grad classes here, you might run a library. Where basically grab this one function from that whole library called from interpolate, regular grid interpolator. And we'll talk more about that when it comes relevant. So okay. Next slide. Oh, I didn't even know I animated that. What's up, Gabe?
Do we have access to these slides?
No. I can post a recording afterwards, but like yes, can post a slide maybe? Yeah, I can do that. Yeah.
Okay. Well, until I can like back up a bit, so I can like finish
Oh.
that regular.
Yeah.
That's fine.
Yes, what's up?
When I reach the I try to launch it with the Python launcher, it just gives me a preferences screen.
Is this like your own personal website or is this your own personal?
I downloaded it on company, figured out that's what I'm supposed to do.
So no, definitely that is how you mainly do stuff, but I want to avoid that because it's gonna cause a lot of headaches. I think with the downloading process. I just think for now let's stick to the online tool because it's much easier to work with.
Okay.
So maybe someone can share on the website, that'd be great. Yes.
So is the font, so we shouldn't use like Jupyter Notebook or anything?
You're allowed to if it works. It's just that I don't want to deal debugging it to be honest. That's fine. And that was like my least favorite part of this class. So honestly, maybe I'm glad it's gone, but not really. Any other questions? Anyways, if your compiler doesn't work, try switching to another one because some compilers might miss some of these libraries. But the one I used online last night, like 3 of them work essentially. So it should be mostly doable. Okay, but once again, as I said, these libraries have functions that we need to run our code later. And if we're all good, I'm also gonna type this on myself later on. So if you can't finish it, don't worry about it. I'll type down again. So next up, the step 1. Once again, I saw the picture from the 2 slides ago. We saw the flow basically in a Cartesian grid, right? So obviously the first thing we have to do is make our grid or make our mesh for this simulation. So in order to do so, here's the line of code that I'll type down and please now don't worry about writing it down yet. What I want to point out is just what each line means. So first, we have n equals 200. Essentially, as I said, we're working with Cartesian grid. So we're basically going to break down the x and y side to be 200 points on the x, like 200 x points and 200 y points. So that in total, our grid should be about like 40,000 points, I think is the number. Yeah. So that's much punching. We're having our simulation. Next, the next 2 lines, I'm going to establish the bounds of this basic picture frame. So we pick that for our x starting, it starts at -4, and x will extend all the way to 4. Line 3, we have y starts at -2, goes up to 2. So that's be our basically our frame, our box, our grid, our mesh. Now, we have like our bounds and how many points we want, but we haven't made the lines like we haven't discretized the grid itself. That's for the next 3 lines coming. np.linspace. np refers to that NumPy library that we installed at the very first line. Linspace from MATLAB, remember, you essentially state your starting point, your end point, and how many points you want to discretize that into. So when you run x, in the red box, you'll basically get the first line. You get -4, -3.959, bunch of other numbers, so it gets always to 4 after 201 or 200 points, essentially. For y, we run np.linspace from y starts by n. You're going to get essentially the first column in the blue box. The first column goes from -2 to -1.9798 all the way till it gets to 2. So yeah, so essentially you make 2 arrays based on how many points you want on the x and then y. Finally, using np.mesh grid, you put in the x and y arrays that are discretized, and you turn your 1D discretized array into 2-dimensional discretized arrays. So once again, in the red box, I have x is red, so red is for x right now. As you see for the first row, that's how the discretized array is laid out row by row. So each row is the same, spanning from -4 to 4, just like how it is on a Cartesian block. Then in blue, which is for Y, as you see, now in this case, each row is the same. It's each column that's different. Sorry, yeah, each row is the same. It's each column that's different. And obviously for Y, it makes sense because in the same row as the Y is constant. So like I said, you discretize your mesh using np.mid mesh grid. Any questions so far? Okay. If not, I'm gonna type this down on my side as well and just have it there. Okay. So I'm gonna grab our libraries up here. So like I said from earlier, and let me grab my other points. So while these parts I didn't post on like the text document, the functions I did put there. So when the functions come up, I'll let you guys know to copy those over. Yes.
I keep getting an error toward the third line. Oh, sorry, your fourth line.
Okay, what's wrong with that? Does it say the library doesn't exist or what exactly is the problem?
It's saying that
This. How can you guys try to collab for me as well? Let me know if it works. Maybe it's because of welcome. Okay, yeah. So collab works. I think it's because it's pasting white spaces. Basically, the way that Python differentiates stuff is through white space, and I'm thinking that's why I'm getting bugged by copy and pasting. So I'm gonna have to start typing as well. But essentially, as you see here, we have the mesh I showed on the slides earlier. And is everyone on Colab right now? Hey, Alex? Yeah.
Yeah.
Hopefully, yeah. So this looks like it works. Let's keep going and see if it works for the plotting function too. I'm really curious about that. Okay. But anyways, that's step one. So we're all good there. Anyone still behind or have any questions or anything? What's up?
Oh, can you go back to the code?
Oh, sure. Sorry about that. Here it is.
Is it from that plot then toward that skeleton?
Okay, for a PyPlot. So PyPlot is it's a class under Matplotlib. Long story short, it's like a function and a function and a function is what it is. Cool. Thank you, Esther. It's good to hear. Thank goodness.
Seems to be running. Seems to be running correct.
Thank goodness, man. Cool. Yeah. This beats anyone here's MacBooks? Oh my goodness. Mac users, you people were the bane of my existence last year because I couldn't figure out the code for anything. So yeah, I did. I said, Juan Mirandis, please help me. And then took care of everything. Okay, but everything's good. I'm gonna go yeah. Still.
Checking my terminal, but nothing showed up.
Oh, basically I added prints.
Oh,
That's all I did. Just see if it works. And as you see, my two-dimensional X array has been printed. All right, let's go next. I'm not gonna full screen because I don't full screen kind of just well, let me try one more time. And I'm gonna switch. I'm just gonna do it not full screen. I'm just gonna zoom in like this. And we're gonna keep going, okay? But we made the mesh, that's really good. Step two. So I mentioned earlier, there was those three basic flow building blocks in that picture, essentially it's free stream, source slash sink, and vortex. We're gonna start with the first one, which is the easiest one. That is your free stream. So free stream essentially, I saw the image A. Flow is just going from left to right. Each line of that free stream has the same velocity, same magnitude, so it's kind of just constant throughout. So, based on that definition, here's what we see. U velocity. U velocity is referring to the velocity in the x direction, so obviously that's where the flow is going, left to right, right? We're assigning that value of U free. So whatever the free stream velocity we want to be, that's gonna be your U. V V it refers to your y direction, your y component for velocity. As I mentioned for your free stream, there is no y component. Flow is going left to right. Therefore, we assign V to equal to 0. So going back to 103, the formula to basically well, long story short, to work with potential flows, you need your streamline functions, potential functions. That is what basically it's what helps you build your flow solution essentially. So it's more for us to obtain that psi value. To obtain these psi values, here's some equations back in 103. You can still remember that. You know, u equals psi derivative over y, v equals negative psi derivative over x, or with respect to x. Sorry. And as you see, as I said earlier, v equals 0 because there's no vertical component. Therefore, this term drops out. We're just left with this term. We're gonna do separation by variable, integration, I think is what it's called. But essentially, when you do so, you bring the dy over, integrate both sides. Psi equals uv, or uy, right? And that's what I have written there. Make sense? So from that logic of what free stream velocity is, we have rederived the streamline equation, and that's what we have there. Now, we're gonna plot that. And when we plot this, we expect to get this. So how do we plot this? I'm gonna show you with my code. So I'm gonna have to copy and paste because I kind of forgot, but it's here. So we copy paste this over, and I'll give you guys time to type it down. I'm gonna remove the print X because I'm not trying to take up more space right now. So let's run back. Let's run that back one more time. We have our u velocity, u infinity. For now, it's set to be 1, some arbitrary number, and that flow magnitude we assign to the u component, because once again, u is the x component of your velocity. So we have u infinity, which is obviously the magnitude that we're expecting, times num dot ones. So num dot ones is actually saying make a 1D or 2D arrays of all ones. And essentially it's like not an entity, but essentially you can then multiply something into it, and every single quantity in your array will be that back. And that's what we're doing. To make np.1 n of n, because our grid is 200 by 200. Once again, if you remember that. And we're gonna fill it all up with u infinity, which is just 1. So kind of not really a waste, but if the value were to change, it's important. Next up, once again, v streamline. As we mentioned, there's no vertical component to your velocity, therefore it should all be 0. That's what we have npi.0, n of n, once again, 200 by 200. After all that, we need to calculate psi. So as I said again, psi is really crucial to our building blocks. That's what we're going to use later on. Psi, or streamline, is equal to that function I showed earlier in the slide, and basically we derived it. It's just u infinity value times y. Now, with that being said, if you go to that the text file I posted in the canvas, there's a function called plotter. Copy and paste the plotter function and put it here for you to use some stuff. So here, so once again, this is what we saw earlier, and I'm gonna paste this plotter function, which is in the canvas directory. I'm also going to time being put to 0. I'll give you. I'm gonna run the code so I can explain why I type this down. Hit run. Okay. Sorry. You need. I'm gonna move this down. So plotter function right above that, and I have the code. That's important. So, as you saw for the image back in the slides, we now have the exact same plot. We have our flow. These are arrow flows. We have our flow going from left to right, all the same magnitude. I guess I can't really prove it, but look at the arrow sides. The arrow size, it's all the same size. So yeah, flow going left to right. And I guess there's one thing I want to point out, which is this red line. So this red line, it's called a contour. It's just a contour line. So obviously for contour line, this is back in like math 21 feet. The contour line, basically every value on the line is the same value. Like if you look at the best example I can remember my TA giving was when you play Zelda, you look at the mountain, there's like circles, and that means it's on the same elevation. Something along those lines. But once again, contour just means the same value. And in this case, this isn't height, this is psi value. So on this line here, every single psi value on this line is 0, indicated by this input or argument here. Okay. And why is it 0? Because when psi equals 0, what must y be for psi to equal 0? 0. And as you see, all the values of 0 are highlighted. Now, if I were to change my contour plot to include psi of 1, what do we expect? As you see, all the y equals 1 value are highlighted because obviously when y equals 1 times u infinity, which is 1, you get a psi of 1. Therefore, all of those values on y equals 1 are highlighted. Same thing if I put -1. As you see, all points -1 are highlighted. Well, I guess the thing I want to reinforce is, once again, at the end of the day, streamline's just paths that the flow is going to follow in a steady case. Given a streamline, the flow is going to follow that path. And obviously for free stream, it needs to travel in a straight line, and that it's being defined mathematically by your psi function. Once again, that's why the psi value is so important, because it gives you the flow paths. Any more questions or copying down the code?
Do I just copy the defined plotter of the return CS? The
Yes, from DEF plotter all the way down to the return CS. Copy that, stays on top of everything else. Yes, yeah,
So yeah, in MATLAB, you need to put your functions like the very bottom. Does Python care where you put your functions?
it's completely reversed. Half before.
For everything.
Yeah, well, before you call it.
But after like we define like for libraries.
Oh, yes, after you define your libraries, yeah. So as long as you gotta call it after libraries before you call it itself in the code.
Okay.
Pretty bizarre, yeah.
It's saying return is an outside function and just throwing that as an error. Return CS bit.
Well, at least for now, I don't. CS is more important later. Can you look at the plot?
No, it's
Do you have a value here? Or is your thing just an empty array?
I just typed in something there.
Um,
Yeah.
just give me 1 minute to this fast. Look at this.
Copy it over.
You're missing these groups. So feature line is after the frequency, you're missing feature line in your artists.
Where did you find
So do
it?
you see I call the stream right here?
Okay, so you go to first.
So you're missing
Go to
this
packet.
argument.
Counting workshop 1.
Oh.
Yeah.
Another word function.
Yeah. I don't really know which one it is.
I'm still third one.
Okay. I think you can go all.
Okay.
I think the first one's Florida.
Yeah. So as I said earlier, we plot the free stream function. On top of that, you see why the psi value is important. The psi value dictates where your psi value, which is your contour, dictates the flow path of your fluid particle. Okay, let's move on. So, all right, that was step 1. We did the streamline function. Now I want to plot sources and sinks. Essentially, if you remember the figure from before, a source is a point in space which flow radiates out, in the radical direction from that point. Therefore, well, 2 things. One is obviously if your flow is radiating radically from the source, we have to think of this in terms of polar vectors, your polar component. Because it's raining from the point, the flow isn't basically rotating or going in a circle. Therefore, your u theta, which is kind of like your rotation, I guess in a way your rotational flow, is equal to 0. And the only thing over quantity is UR, which is your radical flow. Another thing to mention is this equation itself. Sigma over 2 pi r. It's kind of bizarre, but essentially sigma refers to source strength. Higher your sigma value, the more powerful the source is, I guess, the more stronger, more influential the source is. And the 2 pi r refers to the circumference around the source. This is because if you're put basically the circles around your source, each circle, when you sum up the strength at each location, should always sum back up to sigma. So the closer to the source, there's less basically the circumference is smaller, but at each location of your circle, the strength is stronger or higher. The further you away from your source, it has a larger circumference, but then the strength at each location is smaller. So when you sum it up, it equals sigma, no matter what the size of the circle around your source. Does that kind of make sense? What I'm trying to say is the closer to the source, the stronger the flow. The further away you are, the weaker, the less influential it's to the overall flow field. Therefore, as I said, sigma strength divided by circumference, 2 pi r. So once again, because we're working in polar coordinates, which is gonna come up a lot in this class, to be honest, so be ready. We have to use another equation to get our streamline function psi. So I guess I can basically do integration for the integration thing. So U data, once again, that's the flow going around your source. That's 0. Therefore, this equation cancels out. We're just off this equation, VR, VR equals 1 over R, D side, D data. You plug in this term here, you multiply R over, so then R basically disappears because R is on the numerator, the denominator cancels out. Then you integrate both sides by separation of variables, and you're gonna basically obtain this equation here because you basically have a constant. You have sigma over 2 pi times d theta equals d psi. So it's like a constant times your variable equals the other variable. Therefore, psi equals your constant times the variable that was integrated, which once again is d theta. So this equation makes sense. Can you hear? Now, our Python script is currently formatted to work in Cartesian coordinates. Back when I taught Bez class, behavior there, and some other people taught Bez with me. Yeah, that's it too. That's nice. But we made, at least the way I did it was I converted my entire script points to be R and theta. And then for me, this is easier. But we gotta do the reverse this time. Given these polar quantities, we have to convert them back into X and Y. So how do we do that? We use this polar relationships. So essentially, the polar relationship that matters here is, I think it was tan theta, which obviously means tangent refers to opposite over adjacent. So therefore, tan theta equals opposite. So the triangle opposite. So usually the triangle you have is like a twist. Opposite refers to the y component triangle. Adjacent refers to the x side of the component or of your triangle. Therefore, tangent theta equals y over x. As a result, you can redirect this equation here. Make sense? Okay. That being said, all this math being said, it kind of sucks to be fair, but it's important because that's how you get your, the right code, the right equations to code out. With this right code, we can now plot and obtain what what should we get. So once again, here's what you should expect. I have the code provided for you guys in the text file. Once again, I'll tell you which one it is. It's going to be get velocity and get stream function. So get velocity, get stream functions are specifically designed for the source sink. So let's copy those two functions down and paste it into the code.
Is this gonna be before the plotter function?
As long as the plotter function is above everything else, it's fine. So just keep shoving it underneath, I guess. I'm gonna make a new code box, but whatever. So right now, all I do is I post get velocity, pasted get velocity, and I pasted get stream function. That's all I've done so far. Now, I guess I should try to kind of explain how they work. So, get velocity. Your inputs are strength, which is sigma, xs, ys, which refers to the location of your sink or source. So location matters because once again, your flow is radiating from the source, not from the origin of your plot. It's from that source. So you got to specify where the source is located. That's what xs and ys are for. X and y, the big X and Y, refers to your overall Cartesian grid that we made at the very start of this tutorial or lecture. And that's what's being used to calculate your psi values and your velocity values at each point in your grid based on the existence of the stream of the source now. Okay, well, anyways, so yeah, I guess we'll plot and I can explain from there. So with these two things, obviously now I gotta make my source, right? So with my source, I got designate it with a strength, then I got designate with a position. Those are all I gotta do for now. So for source strength, I'm gonna give it 5. These are just arbitrary values for now. For the x location of the source, I'm gonna give it 1. No, a -1. And for the y component, or for the y location, just give it 0 or whatever. So therefore, with like the parameters of my source specified, now I gotta basically make it with respect to my Cartesian field. So to do so, I'm gonna first use get velocity. Get velocity of the strength and values up here. So x and y, once again, this is referring to the x and y from the very start when we made our grids. strength, I gotta basically rename it based on the source strength that I desire. Then XS, the location I desire, and YS, the other location, the Y location that I desire. And so get velocity. So I guess to specify. So once again, definition basically saying we're making a function. We're declaring a function. When you declare a function, there's some things are important. For example, one is what's the name of the function, so that the program knows when you call this, you're referring to this function. So in this case, whenever I call get velocity, it's referring back to this function here. Each function has parameters, and obviously with the parameters, function can then run the coding or the program is meant to do within the function. So those are what the arguments or parameters are referring to. Then finally, at the very end, basically you're saying return these values or spit out these values I desire. And the points for get velocity that I desire are obviously the U component for velocity and the Y component for velocity. That's what's spitting back at me. Okay, so the heck. So return to me U source, 1 second, and V source was to get velocity. Yes, what's up?
Are there those functions that use one massive block of comments above the actual things?
Yes, the comments are just to describe what it does. Basically, this lecture was inspired by it's called AeroPython. I linked it at the end of the presentation, but it's from a professor at Boston University. Basically, she decided to try lecturing via Juniper notebooks, and then Robinson kind of like said, "Oh, it's kind of cool." So he kind of took it and implemented it for this class. So back in the day, most of the projects were based on her lectures, her lecture notes, and her lecture material. Okay. Anyways, any more questions? So I have my velocities. Now I want my obviously psi values. So psi source is going to be equal to get stream function. And I'm going to repaste the same parameters because it's the same source, basically. Nothing's different. So the same source, I get the required psi values. And now, once I get these values, I want to plot it, right? So let me just copy my plot function real quick, and I'll come back to that place. So plotting takes in a few input parameters, but obviously the x, y of the grid that we desired earlier. And then it wants the u velocity, the v velocity, and then the psi value. So we're not working the free stream anymore. We're looking at the source. So we're replacing each of our variables to be based on the source, not the free stream. Talk about that later. And when I do so, I'm not going to run the command. And it should plot me what I want. So here, it plotted me what I saw earlier in my slides. Yes, Alex.
Are you gonna be posting this recording or just sharing your screen share?
No. I think I'm pretty sure I'm recording. It's my first time doing this kind of stuff, but I should be able to post
So this is plotting the source of the thing, or
it. Here.
yeah.
Yes. So basically, what I did was I replaced the input parameters. So these two don't really change throughout this entire rest of this tutorial. These two are the same because obviously we already have our x and y grid that we made up. Change that. The only thing we're going to change are these next four, I guess. The u velocity of the thing we're looking at, the v velocity of the thing we're looking at, and the psi value. Right. That's why I just changed those three parameters. Now, as a result of changing these three parameters, I get the following plot. Right. Our source is located somewhere here. There's like some kind of black hole or something, and just spitting out flow in the regular direction, radiating from the source itself. As mentioned before, if I put a circle here, the strength or the source strength of each location along a circle is going to be very large because you have a small diameter, or sorry, a small circumference. But if I draw a bigger circle around my source, the strength location of each part of the circle is less, but obviously the circumference is greater, and then it bounces out to give you the same sigma value if you were to integrate it over the circle. Okay. So the spread line once again is based on the inputted value here. I put 0, so obviously 0 refers to my equation, but it is your equation is the constant multiplied by theta. Therefore, obviously, if you want psi of 0, theta equals 0, and voila, here is where theta is equal to 0, right? Yes, super.
It's only giving me the plot, original one.
So you see, I said earlier that like when you change the source, can you just run it for me?
It's very confused because I can snap on your lines.
Oh, yes, for white space is really important.
So like.
Okay, let me know if it works after. Yes,
I'm self-limiting.
So he's.
white space, you're the indented, your within your state. So you see how the data lines with term five, term five, the indent, so this is the indentation, so that's fine, your next lines are still indented, you need to unindent. Oh, okay. If you keep it indented, so once again, Python use white space to identify stuff, so how it identifies, for example, in MATLAB, you look at a function, yeah, that's good. When you look at a function, how does MATLAB know what's in a function? It says function and it says n, so it knows to stop. Same with for loops in MATLAB, you have for loop and then it says n. So Python doesn't have n, it just looks at white space. So tabs, basically you are assigning it to something else. So when you tab into the function, it's like, oh hey, this thing belongs to the function. Don't do it unless the function is called. Make sense?
Yes.
Okay.
Wait, can you say that one more time?
So in MATLAB, to identify what belongs to a function, it would be like function, then you would say n. So the program knows, oh, he says n, so everything before that is part of the function. Same with for loops. You say for loop that, you say n. You start with MATLAB that, hey, this section is part of the for loop, nothing else. Python uses indent. That's how you assign something to something else. So when you indent, you're basically saying, hey, this belongs to wherever I called at the very top. And so you keep typing with the indent to keep assigning it to whatever it was before, and then get called unless you call the function itself. Yes.
I might have missed it, but for the last line plotter,
Yeah.
what is the zero mean in the square brackets?
Yes. So I'm gonna change that a bit, like or real quick. The zero refers to the contour value. So like basically I'm saying, hey, at every location where side equals zero, put a red line. So this red line indicates that the side value is equal to zero. So like once again, let me show you what happens when I change this value. Remember, your source function is psi value equals constant times beta. So basically, your psi value is directly proportional to your theta value. So I believe it's in radians. So let's say if I said pi over 2. If I said pi over 2, what should I get? Well, that was exactly what I expected. Maybe it's in angles. Oh, I forgot. Okay, well, let's just say I increased it by a little bit. So when I increase it by a little bit, as you see, the flows or the angle is different, right? That's specifying a larger angle than zero. Therefore, the corresponding side values that have 0.0, that's 0.1, requires your theta value to have be matching in that location. Obviously, whatever this is in 10 degrees, I say 10 degrees here, and it'll give me 10 degrees from another 10. Does it make sense, Gabe?
So why didn't the pi over 2 work?
I don't know. To be honest, I have to do the math, but I'm pretty sure because pi over 2 is obviously the right, like, should be straight up, right? But once again, the formula is psi equals some kind of constant times psi or times angle. So then I would have to divide like the psi value by the constant, which is strength over 2 pi, but that's right now it's low to my parents to do. But you can solve for the correct values. I just didn't want to do it. Do you want me to?
I trust you.
Okay. But let's say for now, like let's just say 0.1 corresponds to 10 degrees, therefore the line is not 10 degrees. That's all I would want to say. Yes.
My stream function is a little bit different from yours.
What is that? Okay. Can you show that your like where like the line?
It's like the array is 1D.2 units to.
So once again, same as earlier, you're missing the V source and V source, which are the size. Yeah. Any more questions? If not, we're almost. Yeah. Oh, sorry.
Getting an error in that, should see this view to some 1D. So this has been since the very first blog, like I never thought that.
Seriously?
I'm
Look at this image on the screen, like.
sorry.
Where does it get?
Like this.
Yeah.
Roll shift different apart? No, sure. Okay. I'm also just calling every time. Actually, after I'll try one quick. So control control or standing business. See, no deficit. Yeah. Actually, this is far like our college. It's now this team of black. Since she's got the suburbs like a little tricky things. I think so. Yeah. It's just it's really cool when it's like it's realizing yeah, the stress is here. At least love the color more than we should have. Yeah. I was just after so I think you were kind of just like please follow. Yeah, we'll try out this. We're not allowed to fill in our company. Try to online units. Stay at home. Yeah, all that is most. You're also there. Second floor now. I'll come back to you. Yeah, no worries. Again, you're a partner for sure. Because the reason I'm saying this is we're almost done. I want to get the wrap up there and go home. You know what I'm saying? Okay. Where'd my mouse go? There it is. Hey, ran away. It's under search, right? All right. So where were we? Okay. So we got pre-stream. We got our. That's good. I mean, I kind of explained the basic of it, but that's just all it is. Has Robson covered this in class yet, or no? He should soon. I think it's coming up. And what about a fluid quiz? I don't know, but
That's it. When I do Python.
all right. Anyways, step 3. This one's really quick. Run through quickly. The whole point of these building blocks is it's kind of like Legos put together and something happens. What the thing is, we'll get there. So essentially, what we're gonna do now is we're gonna combine the effects of 3 different things: free stream, source, and sink. Now, I've already described free stream, obviously, flow from left to right, right? Source, flow comes out of like a point. Now, sink is the opposite of a source. A sink is essentially a point which flow comes into. So once again, same concept. It flow like the smaller the circle around the sink, stronger the magnitude per location. The farther away the circle is, the less strength it has over the circle. Now, maybe it's not too bizarre, but for free stream, you'll flow from left to right, right? So it's kind of just you'll flow here, goes over here. Now sink is different because essentially you'll flow is spawning from this point and just going outwards, right? So you have flow spawning. Essentially, what's going on is you're creating mass by introducing the flow via a source. Therefore, obviously, that is not correct. Like this does not happen in real life. The closest example I think of is in the 2D plane, you have a pipe underneath pushing out flow. That's essentially what's going on. You're kind of creating flow that way. Once again, this is not realistic. So in order to make it realistic, what we're going to do is introduce a sink of the same magnitude to destroy the same amount of mass that's being created by the source. So you got a pair of source of a sink in order to basically destroy the mass that you're creating. That's why we have free stream plus source plus sink. And that's why the source and sink strengths must be equal. So essentially, here's what we're going to do. We have u be inside for the free stream and the source. We don't have it for the sink. So let's make these values for the sink and then add them all up. Okay. Code labs. New code. So same story, sink source. Now, once again, same magnitude to destroy the same amount of mass you created. Negative 5.0. Obviously, next is location. We have x sink. I'll give it -1. Y sink, give it 0, same as source. And obviously, we need to obtain the values now. And we can use the same function, get velocity and get stream function. Because they're all we did essentially is put a negative sign to your sink source and sink location, which is actually positive by default. Get velocity. We're going to assign u sink and v sink to be get velocity of same parameters up here, except I'll change it in a bit. Oh, shoot, no. Here. Everyone copied so far, okay, right? Sink, and sink. So now we have the u and v velocity for the source and sink. Ooh, okay. Then we look at the psi function. So psi for sync, it's going to be equal to get stream function of the same inputs. Okay. So once again, this is how I obtain the values. Now, what I care about is once again doing superpositioning or combining everything. So U total is equal to the U free stream plus U source plus U sync. V total equal to V streamline or V free stream, which we know is 0 by the way. V sync or V source. V sync. Finally, psi total is equal to psi free stream plus psi source plus psi sync. Sync. Now, these are new parameters based on all I've done is based on the XY mesh or grid we've created of free stream, source, and sync. I just put them all on top of each other and combine them. And now we're gonna see what happens when I plot it. Okay. I think it should work. So quick thing real quick. Let me get something that I need. Here. So let's just cover the basics. So we kind of see the free stream function, right? Because we have flow coming here and moving to the right. That's the influence of the free stream building block. See here, at the x equals -1, that's our source. Once again, from the source, flow is coming out of the source. Radical. And here on the right, at √1, that's our sink. Flow is being sucked in there to who knows where. Now, long story short, the flow near the circle or near the source, as I said, is stronger because obviously the closer to the source, the stronger it is, based on the equation that I showed you earlier. Something I think it's like something over R. Essentially, it's like inversely proportional, right? Now, as I said earlier, the further you move away, the less strength, less influence that source has. As you see, at some point, the influence of your source matches the influence of your free stream. Therefore, a stagnation point appears here. That's where, like, equals 0. This cancels out. Same thing for the sink. At some point, it cancels out here with another stagnation point. Last thing I'll mention is because this happens, and basically, at the very top, I basically said, give me the red line where psi equals 0. That's all I said. Wherever psi equals 0, give me. And so at every other location here, psi equals 0. What happens as a result? All the flow being generated by the source remains within this circle and gets eaten at by the source. Therefore, all the mass you've created gets destroyed. So while there is basically we're violating the law of concentration mass within this area, what do we do? We just look outside here. Problem solved. We don't look at problem exists, don't look at it, problem gone. So we just care about the influence outside of this. This here is violating physics in a way, or violating concentration mass, but it's just to make this image this Rankine oval column. Does that make sense? So while the flow in here is janky and not really true, the flow outside of it is relatively theoretically true. Okay. Any questions? Yes.
My code is showing it the identical on zero first machine.
Let's see what's your inputs.
Same ones that you guys are doing much better.
My graph is violating the positive.
Choose.
Oh, sure. He has two sources of masses.
He's going up.
So he's sometimes over
If it was not further, so you run plotter.
some plotters.
Sounds that's true. It is like to fund the steam family. First ones of steam slash cells. Shoot it, I tried to run on.
Yes,
Okay, thanks for happens. No, it's possible. Reach out for it's possible. This thing is possible. Sure. That's right.
No,
I understand.
No, switch was negative.
Yes, I was being like, yeah, that's awesome. It's a long time. It's a lot. Yeah, I was going to last sequences. Yeah. It was true. I don't think what you know. It was one. I think we should see what it's, you know, a lot of them. So keep your mind on. Launch. Yeah. Size of ones. That's all why there's something standing. What? Sure. So I have two shower stations sitting out sinking.
So you put a negative sign because sinks require a negative sign.
Yeah, I have a neighbor side my sink, possibly purpose. And then, oh, yeah, so I put myself also like, or like there's like, oh, sink strength stage one.
Don't worry, when I take this class, this clearly not experience. I also sucks, but it's not.
Or I thought it was.
Yeah. Just you that was the our cap.
Ow, alright. So now we're gonna get a small change.
Oh, yes.
We're gonna now move the location of our source and sinks to be close to each other, right? This is a ranking body, but I want a different geometry. We can modify that by changing these locations. Let source, please modify to negative 0.1 now. For X sink, we're gonna make it positive 0.1. And because I put in different codes, I'm gonna have to click run all because I want to run each different code block because I modified a different code block. So I'm gonna hit run all. So here's what happens. As we push our source things close together, we instead of ranking oval or body, ranking oval, it's more symmetrical now. So this is flow over a doublet or cylinder, essentially. By pushing those two source things together, you get flow over a cylinder. Now, actually, someone actually derived an equation to represent this without the source and sink. Essentially, in this mathematical equation, the source and sink are on top of each other, but instead of canceling out, something different happens, aka this. I'm not gonna cover that right now. I just want to show you that combining these stuff gets you full flow that actually makes sense. But once again, this is flow over cylinder. Flow over cylinder is a very important thing. Professor Robinson will cover this in class, and at least for the homework thing that I sent to him that I recommend the class do, I said that we should work on this. So this is something we should cover. And the reason why I say we should cover flow over a cylinder is because there's actually an analytical solution to this. Essentially, the analytical solution is as following. So yeah, combine to make ranking body, then that. Flow over cylinder. Maybe I'll get that later actually, but essentially there is an analytical solution, and we want to see if the answer that we created for my building blocks matches with the analytical solution. That's the goal right now. So how to do that? The analytical solution is pressure distribution over the cylinder that is equal to something. So we want to obtain pressure distribution over cylinder. I think my first slide starts. No. Let's go to here. Pressure distribution over cylinder is coefficient pressure is equal to pressure difference divided by dynamic with pressure. That's what it is. So to obtain this equation, one thing we can do is use Bernoulli's equation. We're going to assume that we're on the same height, so we're looking at 2D planes on the same height. So we cancel these terms out. We rearrange the equation to obtain that second line there, and as a result, we get that coefficient pressure is equal to 1 minus the velocity at the surface of the cylinder divided by the free stream velocity squared. You can do the math; it'll check out. So we're interested in obtaining the velocities at the points around the cylinder, so we can use them for our calculation. Now, how do we do that? This can require us to use the last function I provided in the text file. Go ahead and take that from me and paste it into your code. Essentially, what I made, not even I made. I'm pretty sure back in the day I Googled this. Me and my class, we Googled this, and then we just used it. All you're doing is essentially you're reformatting the data of your contour, like the red line in all your plots. We're basically taking the data and we're going to reformat it so we can use for our calculations. Yes.
What were you saying? The new X source X sink?
Oh, for the source, negative 0.1.
Yeah.
I split the decimals, and then for the thing, 0.1.
I did that. Produced nothing like.
Or I'll look.
So, when you fill in the plotter in the pond, it's the last one, the five before the tunnels.
That's a mistake. You need to do that, my house, yeah. Oh, yes, okay, so you changed it, didn't work?
I mean, I just changed sources to get that higher thing. Yeah.
Oh, yeah, this is all 0.5. Yeah, so yours wants to do around just one, but
Yes,
it's yours is close to one is the
Yeah.
loss first.
yeah.
We gotta get okay. Let's do it. So that red line that we've been seeing earlier, let's get that data. Okay, I want to finish off Friday's lecture by recompleting the code that I wasn't able to do. I rewrote the code to basically, it was just outdated essentially, but this new code, like I said before, we're taking the red contour line that we see in our cylinder flow, and we want to basically extract the x and y coordinates associated with the red line. This code basically helps us do that, this function here. I guess, long story short, our last three parameters shown here, don't worry about it too much, it's just part of the code reformatting extraction process. Only thing that matters is the first input, which is basically your contour stream, the red line. And that red line we obtain via the plotting function. We have it as our return function, our output. So, plugging CS in here, I say data frame is equal to, run the function reformat contour data CS. And when I do so, what is the df value? What is the data frame that I'm returned with? Well, I'm returned with data frame x, data frame y. And as I said, that's associated with x and y coordinates with the red line. When I plot it with this function shown here, what happens? As you see, the plot shows the red line. We have the red line going straight through where y equals 0, and we see the cylinder here. We're only interested in the cylinder itself. Therefore, we just want to extract the cylinder. Because it's pretty difficult to just extract the cylinder without the line, we're just going to extract the top half of the cylinder because this flow is axisymmetrical. Therefore, we only need one surface of the cylinder to obtain our CP data. And we can do so with this command here. I say that, hey, return for me data frame, in which the data frame is return me the data frame in which this logical statement is true. And the logical statement that I'm specifying is in here. I'm saying y coordinates of the data frame must be greater than basically 0.001. If that's true, then return to me those values, and any other values we're going to discard. So doing so will basically extract me just the top half of the cylinder, and I'll show that with this function here. So just this top half here, that's what we want. So now, as I mentioned before, we wrote this earlier, but I'm going to write it again. We're going to call from this library called basically Scientific Python, SciPy. We're called the interpolate class, and under the interpolate class, we have regular grid interpolators. Essentially, we use this to make functions in which we can then plug in x and y values, and then it will return us, I guess, x and y values with the corresponding value of interest on those x and y coordinates, and it'll essentially do a bilinear interpolation to give us corresponding values based on those bilinear interpolation. So that's these next two lines here. Uinterp is now a function in which, so we call it regular grid interpolate. We specify that we're going to assign two parameters, which is y and x, and we're going to assign it with the value of u total. So we're trying to interpolate for u total based on the given y and x values. And that's going to be basically concatenated and compacted to this function called uinterp. Same thing for vinterp. We're using the same parameters, y and x, but this time we're looking at the v velocity. So with these two functions here, what am I trying to do? So I am now going to make an array to specify all the velocities within that red contour stream, as shown here. I want to obtain the u value and the v values. So basically, it's like a two-column result. First column being the u velocities, second column being the v velocities, and essentially we could solve for u velocities first, then solve for v velocities, and concatenate it to array. But in Python, it's easier in MATLAB than Python. For Python, when you try to concatenate NumPy arrays, which is the array we usually use for computational work, it can become very complicated because all these weird errors appear. So the best way to concatenate in Python is using zip functions. So essentially, we're specifying
for these x and y values that we are interested in. So these are kind of like pseudo variables. They're basically saying fill in those pseudo variables with all of our different x and y values in our data frame. So we're basically zipping it up and then passing it along to this new array. That's what this function is doing. So doing so, as I said before, will return us a 2-column array. I'm gonna prove that right now. See here, first column is u velocities, second column is v velocities. And now that we see that, our function, as I showed on the slide, we're looking at the total velocity magnitude. So we need to basically take the Pythagoras theorem and obtain the resultant velocity vector, I guess, and magnitude from the u and v velocity values. So we do so with this function here. I just take square root of the x velocity squared plus the y velocity squared. That'll give me total velocity, and now my answer is in one column. And from this one column, I can then plot my associated coefficient of pressure, which once again, this is from the slide. I'm going to compare it with the actual answer, the analytical answer, which is here, 1 minus 4 times sine theta squared. Sorry, I forgot to mention this. Instead of sine theta, as I said before, that's in polar coordinates, we're working in Cartesian coordinates. Sine theta is equal to y divided by r, which is the radius of the cylinder. Therefore, I did the math. You do the math, and you would fill in, with this instead. The actual radius of the cylinder is not actually 0.4, but it looked close enough to me, and it gives you a good answer, so that's why I picked it. But you can try different things you want. And now, with my coefficient of pressure based on my my potential flow solution, and based on the analytical solution for a cylinder, I can then plot both and see if they match up. And when I do so, as you see here, my potential flow solution is slightly under-predicting the analytical solution, but is very, very close. And this makes sense because actually the analytical solution for a cylinder is derived based on potential flow theory. All right, that's the end of the lecture.
I'll figure it out and I'll send you, if it works, I'll let you guys know. Not figure it out. But essentially, this code would reformat your contour plot data. So you then basically obtain the x and y values associated with the red line. So you get the x and y values. You would then use this function from SciPy interpolate. So you basically say, hey, you basically say, you're declaring this is a function. Uinterp is a function where I give you an x and y, and you give me the corresponding view of that grid. It'll just do a 2D it'll do a bilinear interpolation. By result, because once again, the x and y values that we obtain are based on the red line, which surrounds the cylinder. You can then get the velocities associated with that surface of the cylinder, right? Afterwards, with your velocities, you do the following here. We calculate the values, as I said earlier. You basically just plug in your velocity, which you'll have a u and v velocity. So you got to do the properties. You take the magnitude of your components. You get your v value. You do the equation at each point along the cylinder, so x and y values, and you get the CT values at each x and y. So as a result, you get to get this. So you're to do it at every single point, not just red line. You get the following image. However, we just care about the red line because that's the surface of our cylinder. So as I said, Professor Robson will lecture about this, but the coefficient of pressure over a cylinder is as follows: 1 minus 4 times sine squared theta. This is based on the derivation of potential building blocks that we just covered. All this will come out with all this will get you the psi function, your u and v values, and then you can derive CP from that. And as C plot starts, so basically 0 degrees refers to your ending point of the cylinder. 180 refers to the starting point of your cylinder. And at your endpoints of the cylinder, you expect the high output pressure, because pressure is highest here because the flow basically just crashes into the surface of the solid, so it has a high top pressure. Then as we go around it, it's going to drop, then come back up because the flow rate has so it crashes into each other or it goes back to the streamline. That being said, in real life, you're not going to get this. This is an analytical solution. In real life, do something more like this. If you take a 109 lab, you probably did the flow over cylinder lab. I used to teach at lab, and then basically when I teach for the lab, I said, stop recording data here because it's gonna be the same afterwards, and then press the shotgun app. So tell your TA next time to take from 0 to 180. I can use these references. AeroPython lessons plan by Dr. Lauren Barbara from Boston University. There's a link here, and basically there's a few more stuff in this thing I want to cover. So hopefully next 2 weeks we can do this again. Then hopefully you guys will show up. But yeah, for now that's it. Any questions? Yes.
In between here next week, any resources we should like use or learn from, or like just to solidify what we've done?
I think Robinson will take. I think Robinson will take care of it. I just want to give a heads up that this is important, essentially, especially the CQ cylinder. I feel like that's really important. But yeah. Anything else? Okay, all right. Thanks for taking me. Oh yeah.
If I were to, like, say, copy and paste this code into, like, VS Code, would it still work the same?
If you have the same libraries,
Okay.
it should work. Right. Once again, this portion we couldn't do the last part together. I guess my function was actually flawed after all. But I'll look into that and let you guys know. If not, thank you for showing up and free to go. Thank you. That's right.